Hi, this is Anul Mahidaria, and welcome to this third session of Introduction to KiCad and FreeCAD at HackadayU. So, last week we completed the track routing of our PCB, and in today's session, we'll see how to add dimensions and measurements to our board. We'll also figure out how to change the origin for the grid and the drill coordinates. We'll take a look at interactive routing, which is pretty useful when you're doing complex boards. We'll see how we can modify the edge cuts layer by adding a more complex outline. As we did in the schematic, we will figure out how to archive the footprints used on the PCB. We'll add them to the custom library and we'll see how we can swap out the library references from global libraries to the project library. We'll look at creating keepout areas, which are parts of the circuit board where you don't want either a copper pore or tracks or both. We'll also look at exposed zones, which is useful sometimes when you don't want mask covering on certain areas of your board. KiCad has had a great explosion of plugins being added in recent years, and some of them are really very handy. So we'll look at a few of them. Once we are through with all of this, we are practically done with all of the circuit board design, and we will see how to plot our layout. This requires us to create Gerber files, and if you also plan to get your circuit board assembled, then you will need position files for all of the surface mount devices. We will view these Gerber files in GerbView before we package them to send off for fabrication. We'll also look at how we can produce PDF files equivalent to all of the Gerber layers that we have created, so we can have a visual examination, or someone who doesn't have KiCad can check out the different layers. And finally, we'll look at how we can export the PCB into a CAD format in preparation for next week's session on FreeCAD. So that's the plan for today, and if there's additional time left, we'll cover a couple of other topics like advanced interactive routing or how to create a footprint from scratch, for example. So with that, let's get started. Alright, so let me start off KiCad. This is where we left off last time with the schematic, and this is where the circuit board was last time around. To add dimensions, you can use the add dimension toolbar icon over here, but you need to choose the layer. I usually prefer to add it on the drawings layer, or most often on the front fabricate layer. And once you click on the toolbar icon, you get a crosshair. If you hover it over a circular element like a pad or an arc, you get the alignment target. Same also when you align it over the endpoint of a line, for example. So let's click on the center of the mounting pad here. And here's the center of the other mounting pad, and that distance is 1.9. Then let's add another dimension from the center of this pad to the edge of this PCB here, that is 0.76 inches. And then the overall width of the PCB is from this corner to this corner, which is 2.8 inches. Then in the vertical direction, the center of this mounting hole to the center of this mounting hole is 1.34 inches. And the overall width is from this corner to this one over here, that's 1.6 inches. So dimensions can be useful when you're trying to share your work with others, or if you want to mark the center point of certain important elements, like maybe for example the center of this switch. Next, you'd like to change the origin. The absolute XY0 origin is somewhere at the top left of your canvas over here. And some board houses require that your origin starts at maybe the lower left corner of your PCB. When you import this PCB into FreeCAD, it helps if the grid origin is at the center of the board. So there are two different origin settings that you can do. The origin point for the grid, which is done using this toolbar icon, and then selecting the center of the board. We know that the board is 2.8 inches by 1.6 inches. The center is going to be 1.4, in the X direction by 0.8 in the Y direction, and I click there once and you'll see a crosshair target that comes up over there and will be used as the center point for this PCB when we import it in FreeCAD. The other thing is to change the origin of the drill coordinates. So that is done using the auxiliary axis origin toolbar icon over here. So click on it once, and depending on which location you want to choose that point, click once, and you'll now notice a red crosshair over here. So that's the origin for the drill coordinates. Let's look at interactive routing. Let's turn off the layers that we don't need. We can hide the fabricate layers, we can hide the courtyards, we can hide the silk layers, and we can also probably hide the bottom layer. Interactive router settings are accessed from this toolbar icon here, and there are three modes. Highlight collisions, click on OK, click on routing, and if I start a track like so and I try and move it around, it'll highlight all of the pads, tracks which it is bumping into. The other one is shove, like so. Once you select shove and click OK and start routing, it'll now move tracks away from the track that you're drawing to make space for it, like so. And you'll notice the other tracks get pushed away as it tries to find the best possible path to go from one location to the other, like so. And the last mode is walk around, where it doesn't move existing tracks but tries to find the best possible path from your location to wherever your destination is by snaking around, like so. So very handy when you're trying to do complex boards. Our board has a plain rectangular outline, but if you want something more complex, let's select the edge cuts layer. And if you want to add fillets, we can use the graphic arc circle icon. And arcs can only be drawn in the counterclockwise direction, so remember that. Let's select the center of this mounting hole, move down until this edge, and then draw a 90-degree arc, like so. So that's one part of our fresh edge. Let's add another one that is 0.14 inches away from here, like so. Start here and end it here, like so. And then let's add another arc over here, 0.14. Start from here. Oops, I need to drag it down because it has to be in the counterclockwise direction, like so, and end it here. And then finally I can use the line tool to draw a segment from here to here. And every time you'll notice the crosshair comes up when it aligns with an element. So here's a modified outline. We need to now reduce the length of this segment. So as I showed you last time, I can select it like so, grab the endpoint and drag it until it connects here. I'll do the same with this segment, select it, drag it, and then connect it to this arc over here. Now this is our zone, so we have to regenerate the zone by pressing B. That regenerates the zone, and if you look at the 3D view now, this is what a fresh outline looks like. Let's quickly do that for the top edge of the board as well. Let's select the arc tool, select the center of this, and because I need to move in the counterclockwise direction, I draw an arc like so. And then another one that's starts from here and ends there. And finally a third one over here. Start off here, go in the counterclockwise direction 90 degrees, click once, and then select the line tool and draw a segment from the end of this arc to the start point of this arc. So with that, we can now, once again, let me hide the bottom, select this segment, grab it, move it and drag it down like so and place it here. Repeat the same with this edge and drag it, move it here, release it. Click home, press B to regenerate the zone, and if you look at the 3D viewer, this is the modified board edge. So that's how you can create more complex shapes other than just rectangular shapes. Let's look at an important action, which is archiving the footprints on this board and creating your own custom project library for footprints. The process is a little bit similar to what we used in schematic. PCB New offers a way of archiving your footprints to an existing library. And if you recall from last time, we have created a custom library of our own where we have stored the two logos that we have used in our board, the Hackaday text and the Hackaday skull. So besides these two, we'd like to dump all of the other footprints into this library. And thankfully that's pretty easy with PCB New. You click on File, click on Archive Footprints and select Archive Footprints in existing library. It asks you to select a library, so we choose Tiny Blinky and say OK. And with that done, if we go back to our library editor and scroll down to Tiny Blinky, you'll notice all of the footprints are now available here. So the next thing we would like to do is we have a library full of the footprints that we are using in our board, but the actual footprints already on the board are still referencing the global library. So we would like to change that like we did in schematic. The best way I've figured out to do this is to go back to eSchema, this tool called the CVPCB, which I said is a little bit redundant, but this is one situation where CVPCB is really useful. If I go to CVPCB, things are a little bit easier over here. What I do is on the left, I scroll down to the Tiny Blinky library. So all of the parts in that library are now visible on the pane on the right side. And what I need to do is in the center pane for each part, you will notice that the library is mentioned followed by the name of the footprint within that library. So the first component is from the battery library and the name of the footprint is battery holder underscore keystone underscore 3002 and so on. And now our task is to replace all of these with the footprints over here on the right. So the first one is over here already, battery holder keystone. So that is the same as this. So we double click on this. Then we have a through hole capacitor, which is radial D8, that is this one. Then we have a disc, which is this one. Then we have 3 LEDs, so that's this one, item number 5, once, twice, thrice. And we have the logo skull and the logo blinky are already from the Tiny Blinky library, so no need to change that. Mounting hole is over here, item 6, so use that 4 times. D out is a 1x03 pin socket, which is here. SPI is 2x03 pin header, which is here. V in is pin socket 1x02, that's item 8. 5 volt is also pin socket 1x02, item 8. So this one. Resistor through hole is this one, the axial resistor with a length of 6.3 mm. Same for the second one. The push button switch is here. The dip 8-pin package is here. And finally the LDO is the SOT223, which is here. So with that done, we can apply, click on OK, generate the netlist. Although, as I mentioned, it is not necessary, but I like to do this. So then we can go back to PCB New and let's first inspect. This is the battery holder. If I click somewhere over it and E for edit to check footprint properties. At the bottom you'll notice library reference is the library is battery and the footprint is battery holder Keystone 3002 1X2032. Let's look at the programming header, E for edit, and this library reference is connector underscore pin header underscore 2.54. So all of these paths are coming from different global libraries. So let's update this board now. The update PCB from schematic or load netlist, either of the two can be run. Let me choose the use netlist. Click on update PCB, yes, close. And now if we inspect the battery footprint, hover over it, E for edit, you'll notice the library reference is now tiny blinky, and the footprint is battery holder Keystone 3002 1X2032. And for the SPI header, E for edit, and same, library reference is tiny blinky, and the footprint is pin header 2X03. So this is how you archive footprints, put them into your project specific library, and then replace all of the footprints on your board with the footprints from your project library. This makes sure that if there are any changes to global libraries now, they won't affect the footprints placed on your circuit board. Alright, let's look at how to add keepout areas. For example, here's the battery footprint, and it is likely that we either may not find a surface mount battery clip for this and might have to use a through hole version, in which case it may be necessary to drill a hole over here for V in. But if you do that, it's going to short out with the ground plane at the back. So we need to add a keep out under these pads. The way you do it is select the bottom layer, select the toolbar icon that says add keepout areas, click that once, and then just draw your keepout area like so. So let's start from somewhere here. It asks you the layer where you want it to be, and there are three options: to keep out or include tracks, to keep out or include wires, or to keep out and or include ports. We don't want any of these three over here. Click OK, and then we can draw the keep out area like so. Once you've done that, press B to regenerate the zone, and this is how it is. The area under the keep out zone doesn't have the copper port now, and we can quickly do that on the other side as well. So let's start here, keep out copper ports as well, select OK, click here, click here, click here, and double click here, and then press B to regenerate the zone. And here's another keep out area over here. You'll notice that there is a track going through this keep out area over here, and if you run DRC, it'll warn you that there is a track inside the keep out area. Clicking on it will focus where the error is, and in order to fix this, we are going to hide the zone by selecting the do not show filled areas in zones like so. And let me delete this track and just draw a fresh one that starts off like so and ends over here. Let me make sure this ground is connected to this track, and while I'm at it, let me hide the bottom and the top silk layers, and fab and courtyard as well, and see if any other ground pins are not connected. Let me use the highlight tool, the second one from the top, and click on this ground track. So I can notice that these two pads are not connected with the track, and even though the zone connects them, as I mentioned last time, I prefer to have physical connections between all pads before I create a zone. So let's quickly add a track there. Let's add a track here that connects this. Let's add tracks that connect these wires from the WS2812 LEDs like so, and that's pretty much everything connected to each other. So escape, Press B to regenerate the zone once. Let's make the zone visible like so. And here we are. We can now run the DRC once again. Run DRC and the error is now cleared. Let's close this and save this. So that's Keepout area. Let's also figure out how to add another zone for the output tab or the center pin of the voltage regulator, the LDO. And to do that, let me start by drawing tracks first and moving this V in track a bit away from here like so that I can make space for the zone. So I'm gonna just make it like so and then delete this track. Alright, so I have some space here to draw a copper port for this 5 volt tab pin on the LDO. So if you remember, add filled zones lets you create zones. We have selected the top layer. You need to click somewhere once to get started, like so. It brings up the copper zone properties dialog box. Layer front. The net is 5 volt. We like to do corner smoothing using fillets with a radius of 20 mil. Zone priority of 0 and the other settings as usual. Click OK and we can now start drawing a zone like so, for example. Click here once, click here once, click once, click here once, and once over here, and finally double click over here. So that creates a zone for the 5 volt. Hide the bottom layer. Now if I already have a zone like so and I'd like to modify it, I can right click on the corner of a zone like so and I can select the create corner option, or you can just also press the insert key. If I do that, I get another anchor point here which can be used to change the shape of the zone, for example. So I can do this. If I right click on that point and use remove corner, I can get rid of it. So let's take a look at this in the three-dimensional view. So view 3D viewer, and you'll notice that the zone is covered up with the solder mask, which means the copper is not exposed. But let's assume that we want to uncover this zone. To do that, you select the mask layer. So in this case, the top mask. Click on the zone icon once. Click at a start point like this once, and it'll show up a dialog box with the layer already selected. And there's really not much settings over here. You cannot add fillets and chamfers, but you can just click OK. And let's draw an outline that matches the copper zone on the top layer like so. And finally double click here. And what I have here is a mask which makes sure that the underlying copper is now exposed. If we look at the 3D view now, you'll see that this is an exposed zone now. So you can add some additional, let's say, solder over here if this is going to be a high current track, for example, or if you're trying to do an artistic board where you have certain areas where you want to expose the copper. Next, let's look at plugins. Plugins are accessed by doing tools, external plugins. Most of the plugins are available from GitHub repositories, and you need to install them in a specific location on your computer. In order to find out where you have to do it, you can start off the scripting console like so. This brings up the Python console. Let me make sure the text is legible like so. And you can run a couple of commands to figure out where the path is where plugins need to be saved. So we start by importing PCB new, and then let's print for PCB new the plugin directory search. and press enter. So here is a list of all of the acceptable folders where I can keep plugins. I prefer putting it in the .KiCad_plugins directory. So once you copy and put a plugin folder within one of these folders, you can then start KiCad, go to tools, external plugins, and do refresh plugins, and it should appear over here. If you'd like to see an icon for the tools, you can go to preferences, and under PCB new action plugins, you can check the box that says show a button. Click OK. Let's check out some of the plugins that I tend to use. I'll just go them in sequential order that they appear over here. Teardrops. Teardrops are handy and useful if you're doing flexible circuit boards, because it creates a necking area between the track and the pad. So it adds something like this. I prefer 50% for horizontal. Click on set teardrops, say OK, and it says it's added 53 teardrops, so say OK. And here, let me hide the bottom copper and the bottom silk, and here's the teardrop added to this pad. You'll notice it doesn't add teardrops to every pad, because if it doesn't find enough space to add one, it just ignores that pad. This has been added as a zone over here, and if I click E for editing this zone, you'll notice that zone priority level is 100, and this is how the teardrops plugin keeps a track of where the teardrops are. So if I want to go back and delete all of these teardrops, I go to plugins, teardrops, and if I select remove all teardrops, it'll remove the teardrops because they are all have a zone priority of 100. So let me do that. Remove teardrops. It's removed 53 teardrops, and they're gone now. Roundr for tracks creates fillets on tracks. You have to start off by selecting two tracks first. So let me choose this. Click here once, shift, and click here to choose these two segments. Then I can go to tools. Roundr for tracks brings up a dialog box where I can set the distance from the intersection, maybe 1 mm. Choose the number of segments and click round. So there, it adds a nice fillet over here. And if you like to delete it, you need to select it like so using the block select. Then go to tools, external plugins, Roundr for tracks, and select the delete option. So that gets rid of the segments, but then you'll have to use the track option to connect this back like so. Next plugin I have is Mask Expander. Again, I need to select a track for this to happen. Let me select this track like so, and if I go to tools, plugins, and solder mask expander, I can set a value and click OK. And what it does is it makes sure that the solder mask is removed from this portion of the track. So if we look at the 3D view, you can see the result of this, which is over here. You can see this part of the track has been uncovered now. So that's solder mask expander. Let me delete that as well. And let's look at measure length for selected tracks. This is handy when you're trying to do length tuning. If you want to know the length of an existing track and then you want to set a new length for it, then you start off by using this tool. Click once, I select the segment. If I click on U, I select that particular track, and if I press I select the whole net. So that's how you select different sections of copper tracks. So if you want to measure this, the length of this segment, click on it once, tools, external plugins, measure length. It's 3.556 mm at 0 degrees. If I click on it once and U to include that track, then go back to tools, plugins, measure length, then the length of this track is 9.5 mm. And if I again go back here, click once, I for the whole net, and tools, plugins, measure length will show me the overall length for the whole net. Wire fence generator adds a series of wires surrounding a track. Let me try and show this here. Select this track once, go to Tools, External Plugins, Wire fence generator. That brings up a dialog box where you can make some settings, choose which net. I like to uncheck this because otherwise it doesn't really place wires everywhere. And once you click OK, you'll notice that after a while it adds up wires, but it also warns you to run a DRC because placing these wires might now be violating some DRC rules. So let's click OK, and we know certain problems already. For example, this wire is too close to the track, so let's delete that. Same with this, let's delete that. And these two wires, because they've been placed over here on this track, have become 5 volts, so let's get rid of those two wires. And here we have a series of wires surrounding this particular track. So that's how fencing works. Let me undo all of this, go back to home, and let's look at the next plugin. Let's look at wire stitching generator. This is different from wire fencing because what stitching does is sprinkles wires all over your board. So if you want to connect a ground plane all over your board, you just select wire stitching generator for the whole board, like so. Set up a few parameters and then click run. After a while it should add wires all over your board, like so. Let me get rid of that too. The last one is really a pretty awesome piece of code. It's the interactive bill of materials generator, and once you click on it, it brings up a dialog box where you make certain initial settings. There are 3 tabs: general, HTML, and extra. In general, you set the location, you give a name format. You can include track zones and nets. It makes for a more pleasing visual experience if you do that. You can sort components in a particular order. You can blacklist certain components and so on. Click on interactive HTML BOM and say generate BOM, and it should open up in my browser like so. And there are lots of visual settings over here. You can look at just the front side of the board, you can look at front and back both, or you can just look at the back, for example. You can choose a different layout like so. You can have ungrouped and grouped BOMs. This one shows just the netlist, so if you click on one, it'll show you where that net is going, like so. So let's look at ungrouped BOM, for example. And then this is a handy table that shows you how many components on your board and how many pads and so on. And you can also export this as images if you want them to. And there are 2 handy columns over here in the BOM list. One is called source, the other is called placed. So if you are working on a board and you placed orders and parts are on the way, then you can check mark these fields. The other column is placed. As you keep assembling this board, if you've already placed a component, you can check mark it like so, and that row gets grayed out. So a really handy tool. It's not just a bill of materials, but also a great assembly tool when you're creating your own handmade circuit boards. So let's minimize this and go back to our board. And now we are ready to plot the final production files that we can send to a fab house for getting our circuit boards made. The way plotting works is click on File, click on Plot, brings up a dialog box. And there are some important settings here, so I'll try and walk you through all of them. First of all, you choose a drop down and choose the format you want. I prefer to first create PDFs, check them out, and then create the final Gerbers. For the output directory, I prefer to put the PDFs in a separate folder. So I open my project folder, create a new folder here called PDF, and ask it to use that as a relative path, like so. Selecting the layers that I need to plot the PDFs for. I definitely want the front and back copper and the front and back silk. Don't need the edge cuts, but yeah, I would like to have the front fabricate layer. I'd also like to plot the border and title bar so the whole page is printed. I'd like to plot footprint values and references. I'd like to include PCB edge layer from other layers, so remove this check mark. Like to include pads from silk screen, so remove this check mark. Check zone fills before plotting. For drill marks, use actual size. and then select plot. If I go to my project folder, Tiny Blinky, here's the PDF folder, and here are the layers that it has created: the front and back copper and silk, and the front fabricate layer. The one more PDF file that I like to create is located under generate drill files. So click on that once, and here's a button that says generate the map file. What this does is create a map of the different drill sizes that will be needed for your board. Default settings are okay for this. Just click on generate the map file and close it. And if I go back to my project directory, there will be a new file here called drill map. If you open it up, you are presented with a list of all of the drills that will be needed for your board, and a legend that indicates where each of those drills will be placed. So this is also kind of handy and useful to check before you send out your file for production. Let me close this, let me minimize this. And now we can make the Gerbers. So first select the plot format, Gerber, output directory. Let me go to Tiny Blinky and create a new folder here called Gerber. Create it and open that path. Say yes to relative path. The layers we need is certainly front and back copper, front and back silk, front and back mask. You need these 6 layers. You need the edge cuts, and that's it. You don't need fabricate or courtyard layers for making a PCB. We don't want the border and title bio now. We need to print values and references. We don't want to force plotting of invisible text. We want to exclude PCB layer from other layers. That's important. You need to subtract solder masks from silk screen. This is important to make sure that if you have any text or graphical elements that are covering or are on top of solder pads, they will be removed in the plot. And finally, this is where the auxiliary axis as origin is useful. If you have set an auxiliary axis as origin and you want to use it, make sure you use this check mark. Otherwise, leave it as it is. Check zones before filling. The other checkboxes, as usual, are okay with the standard settings. At this point, we can say plot. So that plots all of these layers as Gerber files, but we also need to generate the drill file. So click on the generate drill files button and make sure that you have selected Epsilon format with PTH and non-PTH pads clubbed as a single file. For drill origin, if you have chosen auxiliary in the previous menu, then make sure you choose auxiliary here as well. Otherwise, leave it at absolute. Your drill units in mm or inches, zeros format, and that's about it. I think most of the standard settings are good. So just select generate drill file. That creates a .drl file. Close this, and let's just save this. So at this point, we have generated the Gerbers, and we have generated the drill file and the PDF files. The one additional file that may be needed in case you want to get your circuit board assembled, then you have to create a position file, and you do that by selecting File, Fabrication Outputs, and selecting the footprint position file or the .pos file. So select that, select the directory, put it there. ASCII format works, millimeter units, and depending on the board house, if they want a single file for parts on front and back or separate files for front and back. And then we can, let's select a single board file and then generate the position file and close this. So that creates the position file. Let's look at it. It's in the folder Gerber, and there is one position file. It's a text file, and certain board houses want this formatted with certain headers over here. So you might have to modify this file to meet the requirements of the board house. So that's your position file. So at this point we are done with all of the plotting. Let's make sure that the files generated are as they should be by verifying them in GerbView. So you go to the KiCad project manager and click on this icon which says Gerber Viewer. That opens up GerbView like so. And now you need to import all the Gerber files that you've created. File, open Gerber files, choose the directory, choose all of the Gerber files but not the job file. Open. So that's all of the layers here. The next thing you want to do is file, import the drill file. That's this one. Click on that. That opens up the drill file. Now let me hide some of the layers. Here's the bottom mask, front mask, bottom and front silk, and bottom and front copper. So what you see now is the edge cut layer and the drills. And then I can enable the front copper. On top of the front copper layer, this is going to be the front mask, and then finally on top of that will be the silk layer like so. Alright, so let's hide the front layers and look at the bottom layers. Here's the bottom copper, here's the bottom mask, and finally here's the bottom silk, which is here. So re-enable all of the layers, and once things look golden, we can close this. We can go to the Gerber folder and select drill, the bottom copper, bottom mask, bottom silk, edge cuts, front copper, front mask, front silk, and create a compressed archive like so. Okay, now that we have created the Gerber files, maybe it's a good idea to check out if we can actually submit it to a board house and get them fabricated. Let me open up my browser, get a new tab, and we can try submitting it to, for example, Oshpark. They have a nice online viewer that lets you check your submission before you actually approve it. So let's click on browse for files. You can either submit your .KiCad PCB file directly, or you can submit the zip archive that contains all of the Gerber files. Let's take the zip archive, click open, wait for Oshpark to upload and process our design. And here it is. We have the top layer and the bottom layer, and if we continue this, we can order it out and have it delivered to us in a few days. Let's minimize this and get back to our project. The next thing we'd like to do is export our circuit board into a CAD format. And KiCad offers two different options to export your CAD model. You can do either VRML or you can do step. VRML looks pretty because it includes the copper layer and the silk layers as well. The step export includes just the bare board and just the parts, but step is more useful in a CAD environment. The other thing to remember before exporting is to recall that we placed the grid origin offset at the center of the board like so, which, as we noted, was at an XY coordinate of 3 inches by 2 inches. We will use this as the origin for the export of the VRML and the step files. So with that, let's go to export, click on VRML, provide a destination, and if you check this option that says copy 3D model files to the 3D model path, then KiCad will include a subfolder called shapes 3D, which contains the different 3D models for all of your footprints. That results in a smaller VRML file. I prefer including and bundling everything in one VRML file, so I usually don't use this check mark. The other thing to do is provide the grid reference point, which, as you saw, is X3 and Y2. Output units in mm is okay, and once you click OK, your VRML file is generated. Next, let's export the step format. Once again, provide a output path, choose user-defined origin, and set that as X equals 3 and Y equals 2, and you can click on export. It takes a while, and if there are no errors, then you have successfully exported your step file. So having done this, let's check it out and see if those export have been successful. Here's the step file and here's the WRL VRML file. So let's open each one and check it out in FreeCAD. Right click, open with FreeCAD. Okay, so here's FreeCAD. Let me zoom out, get an isometric view. And this is your circuit board in VRML format. You can see the tracks, you can see the silk legend, but this is a single object. You cannot manipulate any of the footprints individually. So let's hide this board by selecting it and pressing the spacebar key. That's how you hide and unhide objects in FreeCAD. And let's import the step file and check that out as well. File, import, step, open. And here's your step file, and as you can see, it doesn't have the tracks, it doesn't have the self legend, but you can expand the model tree like so and look at each individual footprint by selecting it. I can select the radial capacitor, and if I press spacebar key I can hide it. If I press spacebar again I can unhide it. Here's the disk capacitor, here's the LED, and so on. The third thing you can do is file, import, and get the .KiCad PCB file directly without having done any export from KiCad. So FreeCAD is able to natively open KiCad PCB files. Takes a while for it to import all of the footprints. And once you say OK, this is pretty much similar to the step file. You can expand the model tree and you can expand the models to check out each individual footprint and component like so. Alright, so let's close this and get back to our KiCad project PCB new. Okay, with that done, let's see if we can make a custom footprint. The battery footprint that we have selected, as you remember, is just a standard 2032 coin cell battery holder for a single cell, but in this case we want to use two batteries. So let's start off by first searching online, and I prefer DigiKey usually. I know that Keystone has a big selection of battery holders and retainers, so let me just look for Keystone battery. Okay. So under battery products, under holders, we have about 800 items. So let's see if we can narrow that down. We can use the filters. We're looking for two cells and for the 2032 series. So scroll down here. Here's 2032. That gives us 7 options. We can apply this filter and let's see what we have. All right, so 3025-2 is through hole and 3024-2 is surface mount. So let's open each one in a separate tab like so. So here's 3025-2. Let's get the drawing to start with. So here's the datasheet drawing. Let's save it in our datasheets folder like so. Let's check out the 3024 as well. Get the drawing and save that as well. We'll also need the 3D step file. Let's look at documents and media on DigiKey, but I can't see a 3D or CAD model over here. If I can't find it like so, I usually start off with the manufacturer. So let's look at Keystone Electronics 3024-2. Here it is, Keystone Electronics 3024-2. So let's click on step. To download the step file, please enter your mail address. All right, I guess we have to do this. So provide the email address, submit it, check your email for the code. All right, so here's my email. Okay, here it is. Copy the code and paste it here. Enter code. Hopefully I can get the step file now. Click to download. Okay, here's the step file. So we can add it in the FreeCAD folder, I guess. Save step file. Good. So we have the datasheet and we have the step file. So we can close all of this now. So let's open up the drawing that we downloaded. Datasheets 3024-2. That's the surface mount retainer, and here's the information that we need. So there are two square pads of 0.2 inches, and the center pad, they mention a minimum square size, but usually it's preferred to add a round pad over here of a sufficiently large diameter. And the other important dimension is the spacing between these two square pads. So with this, let's go back to KiCad. Let's open up our footprint editor like so. We can scroll down to tiny blinky, and maybe it'll be easier to start with the existing holder and just modify it rather than do everything from scratch. So let's select this footprint and save it as a different name, say 3024-2. Save it. So we have this footprint over here. Let me unhide the pads like so. Okay, so these two square pads are 0.2 inches square. So let's check that out. Double click on the pad. It's 200.7874 mils, and the other one is the same size as well. Okay, so these pads are the right size. Now let's look at the spacing between the two pads. It needs to be 1.339, but that's from one edge to the other edge. We need to have the center to center distance. So get the calculator, and what we're looking for is 1.339 less 0.2, and half of that is the distance from the origin to the center of one of the pads. So let me copy this so I can just paste it directly in the footprint editor. Go back to footprint editor, double click on this pad, and position X instead of 0.50 needs to be 0.5695. Select OK. Do the same for the other one. The previous one was a negative value. This one is a positive value. Select OK. So that's our pads. I guess it's better to reduce the diameter of the center one. So double click on that. It's somewhere around 700 mils. Let's make it 600. There, that's nice. And now finally what we need to do is move these courtyard, silk legend and fabricate layer segments so that they don't go over the pad like so. Let me get the pads in outline mode like so, and we can now select this graphic line, press M to move it, and place it here. We can then grab this segment, drag the endpoint and place it here. We can grab this endpoint or this segment and place it here. So that's done. Then this segment on the silk layer, once again M to move it like so. Select this segment and drag it. Select this segment and drag it. And finally this one, select it, M for move like here. Select this segment and drag it. Select this segment, click and drag and leave it. So that's one side done. Let's repeat it on the other side. Extend it, press home. Let's fill up the pads and let's save this. So we have a footprint in which the pads are as per the datasheet. The outline may not be, but we will see how to do that in the next session when we use FreeCAD, because from this drawing it's not really easy to draw an outline for a footprint because a lot of dimensions are missing. So not much use. We'll have to use the step file that we've downloaded, and from there we can probably make our footprint better. Let me close this. This one is saved, so I can close this. I can now replace this footprint with the new one that we created. So I can click on this, E for edit, and here's the change footprint button. Select that. The existing footprint is Keystone 3002. The new footprint identifier, I open and I select this one. Click apply, click close, and here's your new footprint. Now, because the pads have moved away from the earlier footprint, it's best to delete a couple of these segments and redraw the tracks so that they connect to the anchor point of the pad. So hover my mouse over this segment and press backspace, and hover my mouse over here, press backspace, and this one I can delete. Okay, then let's select the route tracks option. Start here and place a track like so. Start from here, place it like so. Let's just regenerate the zone. Now, once we have changed the footprint on the PCB like so, we are left in a situation where the schematic is reporting a different footprint from what is actually used in the PCB, and this is where back import helps. Just to show you, if I go back to schematic and here in the power supply sheet, if I double click on the battery, you'll notice that the footprint is still being shown as the earlier one that we have already replaced in PCB new. So I can now cancel this, go back to PCB, and this is where back import helps. We do that by clicking on File, Export, and creating what's known as a footprint association file. So we click on that, click Save, and that's done. The next step is to go back to eSchema and now use this option which says back import symbol footprint association. Click on it once, select the file that was created in PCB new, open it, click OK, and we are done. If we now look at the battery symbol, you'll notice that the footprint is now updated to reflect the changes made in PCB new. So this is how you push back changes from PCB and import them into eSchema. We can just quickly make sure that we make everything up to date by creating a netlist, saving it, and I can now leave this sheet and save eSchema and make sure that I also save my PCB. Let's run a quick DRC on it to make sure that there is no errors. Run DRC, looks good, close it. Let's check out the 3D view. So view, 3D viewer, and here's what our board looks like. And we're still missing the 3D model for the battery clip. Now we downloaded a step file, so let's see if we can use that here. I click on this footprint, E for edit, and here's 3D settings. I can delete whatever is there. Click on open folder, navigate to where my step file was downloaded, which was in this folder under FreeCAD. Here it is. Oops, and seems to be a problem with the model because the battery clip consists of two parts, the metal retainer and a plastic insulator. And unfortunately, the drawing we have received from Keystone shows them separated out in space. So we will not be able to use this directly in KiCad. But anyway, let's just try and place it so we get a rough idea of how things look like. Click on OK. Even the orientation isn't as it should be. And although KiCad offers a way to scale, rotate, and offset this 3D model, it is best to do this in FreeCAD so that we don't have to fiddle around here. But for the moment, let me see if we can just approximately place it. So I guess it needs to be rotated in the X direction, 90. Oh, that's the other way around. So maybe minus 90. Yep. So that's the right side up, but now I have to offset it in the Z direction. So let me see. 0.1, 2, 3, 4 is too much, 4 is too less. So 45 is about right. Let's look at the top view, and it needs some offset in the X and Y directions as well. So let's try X first. Let me zoom in, and I think it's pretty much in the ballpark area where it should be in the X direction. Now let's try Y. About the same. Again, needs to be negative, minus 0.04. Alright, so we have it roughly where it should be, but the insulator is still hanging in space. Let's just click OK here, save this, and try and view this in 3D viewer. Here it is. Alright, so we have the metal retainer where it should be, but not the insulator. Let's save things. Alright, so with that we have pretty much gone through every feature, and as I mentioned earlier, there are a few advanced interactive router settings that we haven't seen. So let's see if we can check those out very quickly. If you go to route and look at the different options available, you'll see that you can draw, of course, single track as we have been drawing up until now, but you can also draw differential pairs. In certain cases, you want to have different tracks have the same length. So you can tune different tracks to have the same length using the tune track option. If you have a bunch of differential pairs and you want all of them to be the same length, then you can use the tune differential pair length option. And then you can fine tune the length of the differential pairs using skew and phase. So let's look at these options quickly. In order to show you that, we'll have to go back to schematic and at least add a few components where I can then use it to show you how these interactive routing features work. So let me start by adding a hierarchical sheet. Click here once, click again, and give it a name. Routing. Click OK. Let me escape creating the hierarchical sheets feature and double click here to enter this sheet, and let me add a couple of components quickly. So A, to add paths, grab a resistor and say OK. Zoom in a bit, R to rotate it once, click it once. Let me add the values, so 10K. Let me add the footprint as well. So F for footprint, go to select and choose this eggshell footprint and click on OK. Alright, so now let me duplicate this. C for copy, move it down like so. Copy it once again, place it here. Copy this one, place it here. Now let's draw a couple of tracks. Use the track symbol. Start here, end it here. Start here and end this. And over here, for example, this could be my differential pair, for example. And over here, like so. Okay, so with the wires drawn, let's annotate the 4 parts that we've placed. So here's annotate symbols, click on annotate, and then let's close it. For differential pairs to work, KiCad expects that the pair of wires are labeled in a certain way. So we need to use the net label feature and select one wire, and the options by which you can label this is some name, for example D for data, and then the symbol plus or underscore P, one of these two options. So let's go with D plus and click OK and place it here, and then the corresponding label for the other wire will be D minus or D underscore M. Since we have used D plus, we'll have to use D minus over here. Click OK, place it here. Just save our schematic, create a netlist, although like I mentioned earlier, this is not always necessary. And now we can go to our circuit board layout, zoom out a bit and update the PCB by using this option. Click on update, click on close, and I have these 4 resistors over here. So let's place them somewhere. Move this and rotate it around and place it here. So that's D plus. Here's the other one. So let's grab that, R to rotate it and place it like so. And let's take the other one, R4, click on it, M to move, rotate it 180 degrees, and then let me kind of place it somewhere over here. And then grab the last one, M to move it, rotate it, and place it like so over here. So with that, we are ready to now draw the tracks. Let's first do the ones that are not the differential pair. So start here like so. And let me draw the other one here, like so. Now let's say we want both of these tracks to be the same length. We can do that using the route tune track length option. But before we do that, we need to know the length of one of these two tracks so that we can set that as a parameter that needs to be tuned. So as we saw in the plugins, we can choose this segment, then press U to select this whole section of track. Go to Tools, External Plugins, Measure Length for selected tracks. This piece of track is 23.342 mm. Measure the other one, so select a segment, U to select the whole section, Tools, Plugins, Measure Length 21.310. So they are both of a different length, and let's say we want both of them to be 1 inch in length. So the way you make that work is click Route, click on Tune Track Length, zoom in on this track, right click on this segment once, and you'll get the length tuning settings. Click that. The target length, that's what we need to set as 1 inch, and then you can have settings for a couple of other parameters. So let's select a target length of 1 inch and say OK. And then once I clicked on a segment and I moved my mouse a bit, it tuned it to exactly 1 inch. You'll notice it says here too short, and here it says as tuned. I can increase the spacing like so, and you can see that the length has now become too long. I'm using the number key 1 to increase the spacing, and if I press the number key 2, I can reduce the spacing like so. And I can press 3 to change the amplitude like so, or I can press 4 to reduce it like so. You'll notice that KiCad tunes it to a certain length and gives you the report that this is tuned to 1 inch. Let's then repeat it for the other one as well. Click on this segment and keep drawing it like this until it reports that it has been tuned. Click on it once and that's done. So we have these two tracks that are tuned to a length of 1 inch. We can verify that by clicking on this segment once, then U to select the whole track, Tools, Plugins, Measure Length, and it says this length is 25.4. Let's check the other one. Click on a segment, U to select the whole track, Tools, Plugins, Length 25.4. And that's how track length tuning works. Let's look at differential pairs now. I select the differential pair routing option. Click on one of the two pads where the differential pair starts from, like so. And you'll notice KiCad now draws a pair of tracks instead of a single track. And now I can lay it out like any regular track, like so. And that's your differential track done. Now, if you have a whole bunch of such differential track and you want all of them to have the same length, then we can use a similar process as we used for these individual track lengths to tune the length of this differential pair. And we can do that by selecting the Tune Differential Pair Length option. Once again, before we do that, we need to know an approximate idea of what length we are trying to achieve. So let me select this segment, U for the whole track, go to Tools, Plugins, Measure Length, and this is 100.629 mm. Let's say that our target length is 120 mm. So we go to Route, Tune Differential Pair Length, right click over here or Control L to get the tuning settings. And let's say instead of 120, we want to make it 125 mm. So that's roughly 5 inches. And once again, you can set amplitude and spacing min-max values, but let's click OK. And now if you click on one of these pairs once and start moving your mouse, you'll see that it starts adding meanders over here, and it keeps providing you a report of the existing length. So we keep moving until we hit the target like so. And if you're in a cramped space and you notice that you aren't able to achieve it using this, you can then change the parameters like the amplitude, like so, for example, and click it once, and you have this differential pair which is tuned to a length of 5 inches. Let's verify it. Click on this segment once, click U, go to Tools, plugins, measure length, and it's 127 mm. Perfect. So as of now, there is no skew in this particular pair of differential tracks, but if there was, then you could also use the tune differential pair skew phase option to get that sorted. Once again, you right click, you get the target skew. What's the minimum that is acceptable? You can then move your mouse over here and it'll adjust the length of one of the two tracks until both of them have the exact same length. So that's the advanced options in interactive routing. Before I proceed, let me just delete this whole block because we don't really need this. So it's just a demonstration of the features. So select all of that, delete, click home, save it once, and I'm going to leave the schematic as it is. So that brings us to the close of session 3. If you have any questions, I'd be happy to answer them, and we'll meet during the next office hours.